Hi folks, Titus Murray here from Southern Highland Structural Geology, out scanning out new outcrops at Hilltop in the Southern Highlands. Today's talk is going to be about the Peteke field, which is offshore Taranaki Basin in New Zealand. We're going to be going through how we used fault risk to better understand fault leakage and how it can improve reserves. Hope you enjoy it. Hi folks, we're going to be talking about the Peteke field offshore New Zealand. It's on the western coast of the North Island of New Zealand. Set of fields. They're Cretaceous Rift Basin and just due north of the Maui field, which is the largest field in the offshore Taranaki. So we've got a set of maps from a bunch of different operators at different times, and we're going to be running through those and having a look at them. So the Tui number 1 well was drilled in 2003 and it got a 10-meter column. So this is the Tui field in here with an oil water contact at minus 3650. 3D seismic came through and helped the operators find the Amokura well in 2004 with a 12-meter column with a spill in between these two structures. And then Peteke 3 was drilled in August 2004 and it got a 12-meter column. So what we're going to have a look at is the sealing fault in the Peteke field and how it changes and what impact it makes on the reserves. The two maps were available from this one from Pan Pacific, and it shows the Peteke field, the fault. These are the well paths, and we'll talk about these well paths in a second. But this bounding fault is used to bound the structure. There's an AWE map as well, which is pretty similar. Slightly difference in contouring, slightly difference in color scheme, but again, it shows the same sort of fault running through, bounding the field. So what we've done is we've run into fault risk, and if you're interested in seeing how we've done this work, there's another video on the channel which goes through how fault risk works. And what we've done is we've digitized the footwall trace using the contours of this map for the upthrown side, the footwall of the fault, and then the hang wall of the fault. So the black is the footwall, the grey is the hang wall. And then what we've got is we've got the observed throw profile, which is this bouncy profile here. And this would be a theoretical profile, assuming a consistent fault displacement. What we've done is coloured in grey or blue areas of rough seismic resolution, assuming 20-meter seismic resolution. So you can see that most of this fault is below seismic resolution. And also that we've got ourselves a drop in displacement, and so we're getting a relay ramp set. It looks as though we may well have a relay ramp. So the guys at Fault Analysis Group have done a lot of work, and they continue to do a lot of work on these relay ramp geometry. So this is some outcrop photograph of Kilve, giving you an idea about here's one fault, this is the relay ramp, and then the second fault. So in seismic, you can often accidentally tie this to this, depending on the resolution of the seismic. So that's what this displacement profile looks like, as though we've got a set of relay ramps in there. If we have a look at the Pan Pacific map, it's very, very similar, based on the same seismic, similar interpretation, and again, they end up with this relay ramp. So, yeah, it shows less throw in the New Zealand oil and gas interpretation at the time between the two of them, but we still end up with this distinct relay ramp. The other thing that was available was in the investor relations pack, where it was this line along here, which shows the 4H well and the 3H well, these horizontal wells, and so you can see they're kicked out into here. So these are the two wells. So the heel of this one is down in here. What's interesting, and this is one of the tricks I use a lot when I'm looking at seismic, is trying to look at where I've got coherent reflectors. So what I'll often do is I'll chase through where I've got a zero phase reflector. So I'm looking at the peak, trough, trying to pick the zero phase and seeing, well, where is my consistent reflector? And I'll chase that up and down through the section, looking for packages of coherent reflectors that I can't cross to the fault. Now, in theory, the fault we're talking about is this feature in here. And as we said, we're right on the edge of seismic resolution. The interpreter's gone and put a fault in there. We're fairly close to the relay ramp, but nonetheless, so this is their fault. So to a large extent, based on the seismic and looking at the displacement profiles, my first thing is to sit there and say, well, this isn't a fault. It's a fault propagation fold or a monocline. We've definitely got folding in here, but have we actually got faulting? And it's pretty hard in that scenario to sit there and say, well, I'm going to have a sealing feature here. So nonetheless, what we've done is said, okay, well, we know we've got interpretation error. We know we've got seismic uncertainty. So those two, the error and the uncertainty, can come together to affect the maps. And the maps are similar, same group of people working on similar data. So what we've done is we're running a fault risk model saying, well, what happens if we're taking the maximum displacement? We know that they can get the maximum displacement best, and we've got an approximate length on the fault. So what happens if we run a simple fault geometry rather than the relay ramp fault geometry into fault risk? So the main thing is we've got this Farewell F1 reservoir, and it's 200 meters thick. We've got a top seal which is 215 meters thick. So it really is going to be primary juxtaposition. So it's going to be juxtaposition of the Farewell against itself that would be a feature here. So if we run through fault risk, we've done a Monte Carlo simulation of the Allan maps, and we've put in the oil water contact in there as the validation tool, and we're getting ourselves a 16, 17 meter error. What that means is we're seeing fault risk is suggesting that we're going to get a column way up here, and it's 16 meters down to the observed oil water contact down in here. So we've got ourselves a fairly big error in here, which seems unreasonable. And given we've been optimistic, we haven't got rid of the relay ramp, you can see this really doesn't make sense. So this is the mismatch between the juxtaposition leak point and the fluid contact. So it's been a modest sized field that had an FPSO tied back into together, and it made some. And it was it's a useful well in that respect. But it seems as though that isn't a sealing fault. And given that we're not charge limited, now this is one of the things we think about a lot. Many of the cases we look at, we want to have a look at lots and lots of fields. And the updip 2E and Amokura fields are also field to spills. They're four ways. There isn't a fault component, and they're field to spill. The GNS, Sykes and Fennell, put together a model, and they're suggesting that actually the Maui field has actually been charged up along this fill spill chain that Peteke is part of. So we've got no problem with charge. So then you sit there and say, well, how do we get the fluid contact? What's the important thing in here? So it's impossible for the structure to overfill, and therefore it's likely to extend further to the south. So we've got a number of fill scenarios. I guess we've got the one we've just discounted, that this is a sealing fault. Then we've got scenario A. We've got a modest increase in here of the accumulation. Then we've got scenario B, which is we've got the accumulation extending considerably into here. And then we've got scenario C. It actually extends all the way through to the Amokura field to the south. So the important thing is we're trying to explain the fluid contact here. We can't explain it using a sealing fault in there. So what else is going to explain it? We're going to get fairly close to these, but we're right on seismic resolution. So if the Peteke field isn't limited, these would be our leaking faults. This is the oil water contact at 2660. If we have a look at the saddle, you can see that there is saddle in between here. It's pretty low relief. It's bumpy. It's not we're right at the resolution. Now we start to have a look at Amokura. It's got oil water contact at 2660 as well. So it seems, if we did have a saddle, it would be a fantastic coincidence to have exactly the same fluid contact between the two fields. And we have a clear spill point for the Amokura field. We've got a really clear spill point to the Tui field, which has got a fluid contact at 3650. So just going through and cataloging these fluid contacts, our spill points, and the neighboring fluid contacts, we can start to build up a picture that really this material, this area in here, is part of these two fields. The fields have been on production now for a long time, and in fact, that they might be close to finishing production. This is being produced, but nonetheless, this was probably part of both of these, either one of these accumulations. And in fact, this is one accumulation controlled by the spill point to the south here. So, really, it's unlikely that this feature in here separates the two fields. Quick fault analysis. It's most likely this is a relay ramp. It isn't a through-going fault. This is common to see interpretations that people put in a fault, they segment fields, putting in the fault, and there isn't a lot of thought as to what the displacement is. But, so we haven't got that. And you can see in the seismic we don't have a fault in there. So we're taking out the fault. Despite the differences, we've got two different maps. They both show the same feature. The AWE and PAMPAC maps are pretty similar. So that gives us confidence. If we had very different maps, then we maybe wouldn't come up with the same story. And on balance of probabilities, it seems really unlikely that both Pateke and Amokura would have the same fluid contact if we had a spill point in here. Well-defined spill point to the south. Next accumulation has a significantly different fluid contact, so we've got a sensible understanding about what's happening with that. This has been a case which is not that uncommon in our professional practice, where we look at leaking faults and we end up taking leaking faults out and changing the volumes. It's tempting to put the faults in because it defines the field, but often when you apply the logic about why you've got the fluid contacts where you are, you realize that fault isn't necessary, and you can then increase reserves. I haven't planimetered this, but eyeballing this, it's a reasonable increase in reserves if the field hadn't been produced in that respect. So it's worth having a look at these faults and seeing if you can get features that extend out of the accumulation by removing the fault. Hi folks, I hope you enjoyed the Peteke field. The next talk we're going to be looking at Attic oil within a field in Oman. So I hope you enjoyed seeing how stack pay and fault blocks can be understood.